So another useful thing that we can do using trig functions, and let's go ahead and write them all out. Sine of theta is the opposite over the hypotenuse. Cosine adjacent over the hypotenuse. And tangent is sine over cosine or opposite over adjacent. And I'm not going to write the inverse, the secant, cosecant, and cotangent. They're just the reciprocal of these. But let's look. In our last lesson, we used information in a right triangle. Knowing the angle of theta, we use that information to say something about the lengths of the sides. But another thing we can do is we can use the lengths of the sides and our trig ratios to find the measure of an angle. And we have a new notation for that. So the notation that we're used to, let's use this, sine theta equals the opposite over the hypotenuse. So this is the notation that talks about sine of theta and its relationship to the other sides, or to the lengths of the side lengths. But we could also write this as the sine inverse of the opposite over hypotenuse equals theta. So we're using the same relationship, the same ratio, but this -1, you have to be really careful because in context, I know we're used to thinking that this sine inverse means 1 over sine, but that is not true in this context. In the context where you have sine raised to the -1 of the side lengths, the ratio of two side lengths equals theta, what we really mean is we're working from side length to angle rather than from angle to side length. So you can see that the direction I'm going to solve for something is different. All right, so let's finish up this example, or let's get enough information in this example to be able to do it. So if I have this right triangle and I'm looking, I know it's right, I'm looking for the measure of this angle, and I have an opposite side that's 12 and a hypotenuse that's 15.7 units long, we want to find the measure of theta. So we're going to use this notation, the inverse notation, and we still have to evaluate whether we're dealing with inverse sine, inverse cos, inverse tan, or one of the others. And of course, we're going to do that by just seeing what we're dealing with. Well, we have an opposite over the hypotenuse. So the opposite over the hypotenuse, we know is going to be sine function, right? The opposite over the hypotenuse is a sine function, but we want to use the inverse function to find the value of theta. So I can say that theta equals the inverse sine of 12 over 15.7. And then this has to be discovered on our calculator. Not that one, though. All right, so let's see. If I put in, notice next to sine here, in green letters, I have sine to the -1. That's my inverse sine function. So that tells me I have to use the diamond to get to it. And when I tap the key, I get the sine inverse. And I want 12 divided by 15.7. Now I think my calculator will automatically give me an approximate value. Yes, because I used a decimal here, it'll automatically give me a decimal here. So if I want to round this, I'm going to say that the angle theta is approximately 50 degrees. And of course I can find the other angle very easily because 180 minus 90 minus 50 equals 40 degrees. And so I know that this is 40 degrees and the question mark angle equals 50. So that's a pretty handy little tool. Let's use it to solve a word problem. We love word problems. A chairlift at a ski resort rises at an angle of 20.75 degrees while traveling up the side of a mountain and attains a vertical height of 1,200 feet when it reaches the top. How far does the chairlift travel up the side of the mountain? Well, first, let's draw a picture. So if a chairlift rises up the side of a mountain, the mountain obviously can be below the chairlift, that part doesn't matter, and the angle of elevation of the chairlift that the chairlift is traveling is at 20.75 degrees, and it reaches a vertical height of 1,200 feet. How far does the chairlift travel? Well, what we're asking is the actual distance the chair travels as it moves along the hypotenuse toward the top of the mountain. This is easy peasy to figure out because really all we're looking at is the side length, or the length of the hypotenuse. We have an angle, we have an opposite, and we have a hypotenuse that's unknown. That means we totally know how to set this up. We're looking for opposite over hypotenuse, and we know that that's the sine function, and the sine function is for the angle. So let's solve this for the hypotenuse. I'm going to multiply both sides by the hypotenuse, so I get opposite equals hypotenuse times sine theta, and then I'm going to divide by sine theta. So that tells me that the length of the hypotenuse can be described as the length of the opposite side divided by whatever the sine of theta is. Now I can plug in my values. The opposite side is 1,200 feet, and sine of theta is the sine of 20.75. So let's get out, I'm going to have an approximate value. Let's get out our calculator. So let's find the sine of 20.75 first. So that's the sine function is yellow. 20.75 is 0.3543. So 1,200 divided by the sine of theta equals 3,387, and I think that's a close enough approximation when we're talking about feet on a mountain. So 3,387 feet. Good golly, Miss Molly, that was fun. Let's do it again. A sightseer on vacation looks down into a deep canyon using binoculars. The angles of depression to the far bank and near bank of the river below are 61 and 63 degrees respectively. If the canyon is 1,250 feet deep, how wide is the river? So first things first, we need a picture. So you're standing at the top of a cliff or a canyon that's 1,250 feet deep. So you're standing right here and you're looking with binoculars down into the canyon. And in the canyon there's a river that you can see both banks of. So you can see one bank here where the orange line intersects, and you can see the other bank right here where the green line intersects. And the angle of depression, and what that means, the angle of depression from your perspective out of 90 degrees, the angle of depression is 63 degrees for the green bank and 61 degrees for the orange bank, which of course makes no sense whatsoever because I've written it incorrectly. So the angle to the far bank is 61 degrees and the angle to the near bank is 63 degrees. That makes a lot more sense. Okay, so what we want to know is what is the distance across the river. So the angle that we have to, the only triangles we have to work with include the right angle straight below you into the earth, and we're going to have to calculate this twice. We want to first calculate the length from just below you to the far end of the bank, and then calculate the length from just below you to the near end of the bank, and this distance here will give you the width of the river. Okay, so the next thing we need to figure out is which angles or which trig functions are we going to use. If I'm using angles here, where the hypotenuse is the distance to the outer and inner edge of the bank, then I'm using adjacent, because these are where the angles are, adjacent over opposite. We don't really care about the hypotenuse at this point. We only care about the opposite distance and the adjacent. But before I set this up, notice that these angles are not part of the right triangle that I'm looking at. That's okay. I'm just going to translate my 1250 feet over here for working, because they are angles of depression. Let's try not to scratch over top of the numbers I'm using. And so I can use this right angle as my reference. So I want to find first the green triangle, the measure of the green triangle. And what do I want for the measure of the green triangle? I want to know, well, I want to know from down here, but the distance across here is exactly the same as the distance across here. And so from the perspective of 61 degrees, this is the adjacent. In fact, from the perspective of 63 degrees, it's also the adjacent. The hypotenuse I don't care about, but the opposite, 1250, I do care about. So I want to find a ratio or use a ratio that involves the adjacent over the opposite. Okay, well, that's actually, I think I don't want to use that one. I think I want to use opposite over adjacent. That would work out just fine too, but the adjacent over the opposite is an inverse trig function, and they're trickier to use on my calculator. So I just want to make sure I set up one of the primary trig functions. So opposite over adjacent is tan theta. And again, before I start plugging numbers in, I just want to solve this. I want to set it up. So I'm looking for adjacent. So I'm going to multiply both sides by adjacent and then divide both sides by tan theta. And so I get adjacent equals opposite over tan theta. So now I can plug in my values. The opposite for the green triangle is 1250. And tangent of the angle, the green angle, is 61 degrees. So now I just go right to my calculator. First, I'm going to calculate tangent. That's the gold button here. The tangent of 61. Darn it, gave me an exact value. No big deal. I just push my diamond and enter. Now I have an approximate value. So now I can do 1250 divided by, just going to come up here and capture my approximate value, and that's 692.88. I'm going to round that up to 693. So it's approximately 600, oh, let me keep my colors going. So this is approximately 693 feet. Now let's do the same thing for orange. Now notice that the setup for orange is exactly the same. So I can say that the adjacent for the orange triangle is 1250 this time divided by the tangent of 63. So come back over here. Tangent 63. And now I want to divide 1250 by that. $636 or 637. So this is approximately 637 feet. And the last thing I have to do is subtract 637 from 693, and that equals 60, oh, I'm not even going to try to do it in my head. 93 minus 37, 56 feet. And it's approximate, if I'm going to be careful, it's approximate. Since these are approximate, then 56 feet is approximate.